It's about malware clustering. I'm Srini. I'm from Alien Vault. I'm basically a data science guy trying to look at network packets and analyze malware based on their static and dynamic features and other features, and try to cluster them and do other things to derive better insights about the malware. And in turn, after getting better insights, you can do a lot of nice things with it. I'll explain all of them as we go. And please don't hesitate to raise your hand and ask questions in the middle, because this is going to be a bit of sequence of mathematical operations on how you achieve your results. So I would like you to ask questions as we move forward. Need for clustering malware. Has anyone tried to cluster malware, or would you know what benefits you would achieve if you do so? Sorry, what? Yeah, but that's getting more into the malware analysis itself, which is done by malware researchers. But this is from a data science perspective. If you, for example, if you cluster malwares, you would know what are the variants of a malware present today. So it will be all the more nice if you cluster them on a periodic basis, like once a week or once a month or every quarter. If you keep clustering and just look at the clusters and see the changes in the cluster snapshots. You'll say, hey, I've seen like 7 clusters in this quarter, and 2 quarters later you see 8 clusters, and it's like you'll see what's going on. Is this and there's a new small cluster out there that could be some new malware which has begun spreading out. That's one thing. The other is, once you cluster, you can learn some of the salient features in a cluster, and once you know the salient features, you could do a lot of very nice things with it. You could write just one rule to detect that whole family of malware, rather than writing many rules to detect them. That's one thing. The other is, once you have this whole clustering mechanisms, the whole pipeline, the whole algorithm developed in-house, the good thing is typically for antivirus companies and researchers, what they can do is, using this pipeline, they will be able to detect new malwares, very new malwares, not seen before at all, as early as possible, write signatures for it, and push it to their clients, so that their clients can thwart those attacks as early as possible. So all this has to be done very quickly rather than very late. The key to doing this quickly is to analyze millions of samples every day and compute the clusters, compare the clusters with previous cluster snapshots, try to find anomalous behavior, and then just compress all these things, give a very few interesting malware samples to malware analysts who can look at it, write very good signatures for it, and quickly distribute it. This needs to be done. This pipeline is essential and has to be done very quickly. So you need to have this massive parallel pipeline in place to do all these things. So those are very nice things to do. What is done today to address this scale problem? Typically, what people do is they will study the static and dynamic behavior of every malware using some kind of tools like IDA Pro or similar tools. They look at the static and dynamic behavior, and based on that, they'll start writing rules. And once a rule is set, they'll try to test it on some known PCAPs, some good PCAPs, some different malwares, and some goodware. And once they have a reasonable amount of satisfaction, they will release it to their clients, so that it's kind of it helps in thwarting those particular malwares and some of their variants. It has to be done very, very carefully. So you have to choose what static behaviors to pick and what dynamic behaviors to pick, and based on those, you have to have your cluster. So clustering is not like it's not generic. You you have to know well in advance on what basis I'm going to cluster the malware. Am I going to cluster the malware based on just the dynamic behavior? If it is just dynamic, or am I going to do it just on HTTP and HTTPS behavior, or should I include DNS based as well, or forget all dynamic behavior? I can also cluster only on static behavior, what files were written, what registry entries were deleted or edited and stuff like that. So you have to first think about the business value, and based on certain priorities, you make your decision on what basis you must be clustering these malwares. And once you have that in place, then you can slowly move ahead. So the key is you have to know this in advance, prioritize it, and then start breaking it down into smaller manageable pieces. So what is a good analysis? You have to do two things from machine learning perspective: feature selection, the other is feature engineering. Feature selection is, once you have, let's say, a typical tool to disassemble your malware, you can see the static and dynamic analysis. Pick and choose what features you want that represents the crux of that malware. So that is feature selection. Whatever is there, you pick and choose. That's it. No more, no less. And then comes feature engineering, which is a little add-on, but extremely powerful for machine learning purposes, which will give you which will boost the performance of your algorithm. So to do feature engineering, you must really talk with the domain experts and say, hey, okay, before I go there, I need to tell you what feature engineering is. So you have to combine different internal features itself, combine them in a linear way or in some polynomial way, and then say, okay, if this, and this occurs, then I'll have a score, internal score for it, and this score will be my derived attribute. It's not an inherent attribute, it's a derived attribute, basically. Or this value plus log of that value plus, and have some other bucket of that, the third value is something very special, which is very unique for this particular class of malware. Things of that sort. That's what I call as feature engineering. To write good signatures, the signature must be specific enough to capture the malware that it was written for. And it must be generic enough to catch the variants of the same malware. It could be variants which was written before or new variants that might come tomorrow. It must be generic enough. And always you strive for 0 false positive and 0 false negatives. These two are extremely hard problems, but I'll go through some techniques which could help in doing so. Some of the approaches to clustering malware are these: hash-based, hybrid, using function call graphs, and using the opcode of the malware itself. I'm not going to talk about function call graph and opcode. It could be a talk on its own. I'll very quickly go through hash-based and hybrid, and we can iterate over it for more detailed discussions, step-by-step discussions. Hash-based, okay, before I go there, this is how a typical analyzed malware file looks like. So if you run it through a cuckoo sandbox, you will get a JSON output, a JSON file. The JSON file will have basically two big sections. One is the static analysis section, and then the dynamic analysis section. The static analysis section will tell you what files were written, what files were deleted, what files were edited, and stuff like that. And then the dynamic analysis, like this, shows what DNS requests were sent and received, and what HTTP traffic went through, and many other details. So this is just an example how a cuckoo analyzed malware result looked like. And this will be the input for my clustering. So if I have a million malware, I'll first run it through cuckoo sandbox. I get the analyzed JSON output like this. and this will form the basis of my clustering algorithm. So what do you do is now the problem essentially boils down to document clustering. You have 1 million documents, just cluster them. It's unsupervised clustering. Nobody tells you that these 10 documents belong to malware A, these 100 documents belongs to malware B. Nobody tells that. You have to cluster them. To do that, there are several techniques. The first one is hash based. Some of the concepts I will go through are shingling, min hashing, locality sensitive hashing, and bit vector matrices. Shingling is essentially tokenization. How are you going to tokenize the given documents? So every step needs a lot of fine tuning and playing around to suit your environment, your input. So you can tokenize it in every 4 characters, 8 characters, whatever it is. So you have to play around with it to see which is good for you. That's essentially shingling. So once you shingle, let's suppose that 3 shingles works for you. Great, fine. If they are very short set of strings, you can move on with it. If the shingles are very long, you have to hash them, because to make it smaller and more conducive for computers to crunch. If you shingle them, you may run into some problems. Let's suppose that you shingle, let's say you have 100 documents, 100 such files. You are shingling each one of them into 3 shingles, and you have all these shingles. So the presumption of clustering is this: if the shingles of document A and document B more or less matches, these 2 documents are perceived to be similar, right? We have to be very careful there. It's not just any document. It's not like a novel or something which we are trying to cluster. We are trying to cluster documents such as this, which has certain sections in it, nice sections. DNS entry, files added, files deleted. Malware A may have files added like file A, file B, and file C. Malware, and then files deleted will be file X, Y, and Z. In malware B, it may be quite opposite. But if you blindly shingle them, and you might end up saying that the algorithm will end up showing that malware A and malware B, putting them into the same bucket, in the same cluster, which is wrong. So you have to do a lot of pre-processing there. You have to pre-process in such a way that the next stage would have a more granular information, which will exactly tell which shingles belong to which section. After doing that, how are you going to decide whether 2 documents are similar or not? There's one way, which is Jacquard similarity, very similar, very commonly known technique called Jacquard similarity. What it does is basically gets the vectors of these 2 shingles and then tries to find the intersection, and then divides that by the union of these 2 shingles. Very simple and powerful algorithm, but it has a very bad inherent property when it comes to scale. If you are doing 1 million documents, it has to do nearly n into n minus 1 by 2 times the comparison, which is pretty long. Right? So, for example, for 1 million documents, it has to do 5 into 10 power 11 comparisons that will take more than 5 days. And for 10 million documents, it will take more than a year. So, you don't want to go there, go in that direction if you are trying Jacquard similarity. Don't ever try to do one document versus the rest of the documents, then the second document versus rest of the documents, third document versus rest of the documents. No, it doesn't work. It can't scale. So how are you going to address this problem? Here comes the magic: min hashing and encoding. You have to do a lot of this, play around with different kinds of min hashing and different kinds of encoding to ensure that your intermediate intermediate results are conducive for your computer as well as for scaling. So the main idea behind min hashing is to converge large sets of text into short signatures. And the beauty of min hashing is when it converts these large text into smaller representations, it preserves the similarity. So you use min hashing. After min hashing, you have a smaller signature, right? Smaller text which represents the larger text. But still, it is text. You don't want to deal with text, you want to deal with numbers, because machine learning algorithms always deals with floating points. Always. You can't get away from that. So you have to convert them into some kind of floating point operations, right? Convert them into, sorry, you can encode them. You can encode them into beautiful 0-1 bit vector matrices. Once you have bit vector matrices, you can basically map your input documents as a beautiful matrix like this. So each column is a document by itself, represented by a 0-1 bit vector, and each row is a shin. Right? Again, now after doing this, what are you going to do? Now you have these documents, which is each column is a document. Again, the question is, you want to find similarities between these columns now. That's basically similarities between the documents. Again, scaling problem arises here, right? You have these so this is linear one-dimensional vectors from top to bottom. Each is a document. You have to compare this vector with the rest of the vectors, this vector with the rest of the vectors. Again, the same polynomial complexity problem, quadratic complexity problem. But the question remains, you have to find similar columns. Then comes another trick, it's locality sensitive hashing. So people have been using hashes for decades. What do you use hash for? You use hashing for the integrity during data transfer, for getting indexes in databases, and for encryption of data at store, right? at rest, right? And the fundamental premise under hashing is when you hash two different items, the result of the hash must be very different, right? And here in the locality sensitive hashing, and for our purposes, the needs are very different, polar opposite. When you hash two very closely similar items, the result of the hash must be the same. Even when the input is slightly different, the result of the hash must collide. It's a very, very different hashing algorithm, set of hashing algorithms, not your normal day-to-day hashing. That's where locality sensitive hashing comes into help. It's basically a probability distribution over a set of items, where when you hash, it will give you two different probabilities. One is, for example, here I say R, CR, P1, P2, right? So if the distance between the two documents X and Y is less than R, R1, or less than R, then probability of the hash of X is equal to the probability of the hash of Y, will be greater than some probability P1. So the lesser the distance between two documents, the higher is the probability of both of them being in the same cluster. And if the documents are dissimilar, then when you apply locality sensitive hashing, the probability of them falling into the same bucket will be very, very low. It's a beautiful thing to have, right? Not your regular hashing. So you use LSH on this bit vector matrix, and before that you have to ensure some other stuff. Make sure the hash of your signatures are able to fit into your RAM. Otherwise, again, you fall into certain problems. And once you play around with different LSHs, and if you're comfortable with one particular LSH, apply that. So you can do, once you do that, then it will be much faster to go over and find similarities between these documents in your bit vector matrix. And once you do that, you'll get a nice n by n matrix where you see the diagonal is all 1, which is where the distance of each, I mean, it's documents, right? Like both x and y axis are documents. The similarity between the documents are 1 when they are similar to each other, and the other floating point numbers indicate the extent of similarity between two documents. The higher the number, the greater is the similarity. Once you have such a nice similarity matrix, you are almost all set to cluster them. Hoping that the similarity matrix is small enough to fit into your machine, then you can apply clustering techniques such as spectral clustering or affinity propagation or some kind of belief net clustering to cluster them and get beautiful clusters like this. I'm not going to talk about cluster evaluation. That's a very different topic, and it definitely needs its own set of seminars on that. But the pipeline, the ideas has to follow these steps to arrive at a decent clustering. The belief net algorithms behave this way. So, for example, you have a set of 100 points and you want to cluster them. Nobody tells you, okay, nobody gives you 100 points and tells, okay, give me 7 clusters out of that. This is unsupervised. So you are given some random number of points, and the algorithm has to figure out the best number of clusters and provide high quality clusters. So what it does is randomly chooses, out of the 100 points, it randomly chooses like k points, let's say 8 points, as cluster representatives or cluster heads. And once you have these cluster heads, what it does is it does two things in a lockstep fashion and iteratively until the result converges. What it does is, first thing is these representatives, they will send messages to all other members in the input data and tell them, hey, I want to represent you. Once the message is received by the other data points will send back messages to the sender or to the representative telling their preference for that guy. He will tell, okay, I like you to be my representative, or he will say I deny, and he will, and this happens in a lockstep manner in parallel. For example, all the 8 points, all the 8 representatives will send messages to all other data points and say, hey, I want to be a representative, and all other data points will send back a response stating their preference. And then once this first lockstep message exchange is done, it goes to the next iteration, does it again, next iteration, does it again, until there is no thrashing. Thrashing in the sense that in k-1th iteration, this member A will prefer X to be its cluster head, and then the kth iteration, this member will be in Y's would prefer Y as its representative, and k+1th iteration goes back to this guy. So it keeps going back and forth. The algorithm wouldn't terminate. So you have to have some kind of termination condition. Either fix the number of iterations as 100 or 5,000 or something, and deal with the results and go on, move on, or find certain other mathematical techniques like what I do is I go into the matrix itself and slightly adjust some certain epsilons and stuff like that, so that it kind of converges quickly without all this thrashing happening. So once you take care of all your matrices, then you are more or less bound to get a decent cluster. That's about hash-based clustering. Questions before I move on to hybrid-based clustering? Yes.
So if I'm not a research organization or anything, so a typical company, how do we adopt these techniques to?
Well, yeah, it's difficult to, well, you can adopt the techniques per se as like, you can learn, okay, this is kind of directions, these are the steps in a pipeline. But when it comes to machine learning or data mining, I haven't seen a single algorithm where I can just buy from a vendor or something and just plug it in and it works magically. There are two very essential things in machine learning, very, very essential things in machine learning. The number one is pre-processing and feature engineering. Without it, you are pretty much guaranteed that you will not be satisfied with your results. That's one thing. Feature engineering, feature engineering, and feature engineering. Either do it yourself or talk to the domain experts, get to know what features need to be there, what combination of features need to be there. The second with machine learning and all these things is fine-tuning. You have to fine-tune. There's nothing you can just buy off the shelf and get magical results. You have to fine-tune. You can spend an entire summer just fine-tuning certain hyperparameters, get an intern to do it, and hopefully it works after the end of the summer. So you have to fine-tune. There is no other shortcut to this. There are some nice algorithmic techniques to find the right set of hyperparameters, but only for certain cases. If you have a search space which is conducive enough, you can have grid search and other kind of search mechanisms to search for the right set of hyperparameters where you don't have to do the experiments. It will run all these things parallel, find the right set of hyperparameters, and you can just plug it in, and your random forest classifier is amazing. If you don't have that functionality built into, let's say I use scikit-learn's all the libraries in Python scikit-learn and R for all my gut feeling verifications. If you don't have that, it's a tedious process. You have to fine tune. There's no other way. And you better document what you do, because somebody who is coming down the road, he wouldn't know what the hell you did and why you put like 0.637 there. Nobody knows why you did that, right? So it's about experimentation. There's just trial and error, and actually, at least some kind of smart trial and error mechanisms. So that's about hash-based clustering, and here's a summary of it. So to summarize this, you have these documents. The first step is you kind of tokenize them with shingling. After the shingling, if they are big, you can hash them itself, then resize, compress those single hashes, then you vectorize them, create bit vector matrices, and then create summaries of those columns. And once you do, if the summaries are large, hash them again. Okay. Once you do that, then apply locality sensitive hashing, which is very, very powerful. Once you do that, you are in a good position to create a similarity matrix. Once you do the similarity matrix, then you can apply some nice clustering algorithms to get clusters. The question is, all this works on a single memory. If I have to cluster 1 million documents, and if your hardware cannot support it, then you will face some difficulties. So how are you going to do that? Yes?
I have a question about this slide. So when we're talking about malware docs, like what all would be in there?
The documents is the one which I showed you, like this.
Okay.
Just JSON documents.
I see. Okay.
This is the output of a cuckoo sandbox or something like that. Okay, which will have a nicely structured thing. It's nicely structured. So we are all happy. No problems out there. So if you want to parallelize There are techniques, but you have to implement them on your own. There are no known libraries out there, as far as I know. You have to do it, and you can utilize it on a GPU or something where you can nicely parallelize such algorithms. But remember, when you begin to parallelize this, for example, clustering is not, certain kinds of clustering algorithms are not do not lend themselves nicely to parallelization. K-means is embarrassingly parallel. Finding mean of a billion numbers is embarrassingly parallel, as against finding median. If you want to find median, oh, forget it. You can't get an accurate answer. You can only approximate it to a certain degree. So you have to be careful there. And that is about hash-based clustering. Hybrid approach. In hybrid approach, you basically take two sets of features. The one is the static set, the other is the dynamic set of features. Many malware analysts look at all these two in a sense. They have it in their head and try to work out their way to write signatures, right? And also look at the packets. So from a PCAP, if a PCAP has 30 packets, they try to filter off the benign packets, look at the one or two packets which looks very interesting, and then try to write a signature on that. Hybrid approach clustering is also on the same premise or assumption that similar looking documents tend to be clustered together, right? So deleted files here and set of deleted files there, if they have more or less the same file names, yeah, great. Edited files, set of edited files here, if they look more or less the same, that's good. DNS entries, they look more or less the same, that's good, stuff like that. So again, pre-processing needs to be done very carefully and methodically. So you do feature selection first. F is a set of features. These are inherent features within your document. And then comes feature engineering, which is derived features, which you get out of both algorithmic techniques as well as from domain experts. You get a set of engineered features or derived attributes, and then comes the union of these two, with which you are going to work, basically, a set of features. So what you do with this? Let S be a set of features for your whole corpus. So let's say you have 1 million documents to cluster. For each document, let's say you have, when I say S1 is one sample, S2 is another sample, S3 is another sample, a document representing that sample, basically. So you have n documents, n samples, and from these you are going to get only, so for each sample you are going to extract only k features. You don't want to make the mistake of selecting all the features in a given sample. There may be like 2,500 features in a sample, out of which probably 150 only are significant enough to give a high signal to noise ratio among the 1 million documents you are trying to cluster, right? So you have to be very careful in selecting the features, both feature selection and feature engineering. And once you select the features for your problem space, then do the same thing for all the 1 million documents. Just select these set of features. You have a vector of features for all the 1 million documents. You create a nice matrix out of it. The matrix would look like this. Look carefully. Is Fk in the first one, it's Fl, and in the next one, the K again, then Fl in the next one. So for every document, the kind of feature selection you do, I mean, the number of features you extract could be different. You can't always have the exact number of features. In certain malware files, you will see some other attribute which looks to be super important. which may not be present in the rest of the document. So you have to include that, right? So you have all these inconsistencies. And matrix manipulation doesn't like these inconsistencies. So you have to deal with matrices back again, right? So here comes both mathematical and domain expertise. So how are you going to deal with these feature imbalance among your data set? So for example, in one malware you do not see a referrer, and in the next malware you do see a referrer. So what are you going to do with that vector which does not have a referrer? Are you going to substitute it with value none or a 0 or a null entry or a blank space? And if you do any of this, how is it going to affect your matrix operations and eventually your clustering results? You have to think about that. Are you going to impute some value there based on previous historical 1 year worth of history you have? Are you going to impute something? Imputation is basically predict, kind of based on some history, based on some statistical distribution. If you predict, hey, I mean, I've seen so much, so mostly this referrer is common, just plug in that referrer there. Are you going to do that? You don't want to, right? At least try to minimize those kind of habits, right? We can talk about that a lot, but the crux, I'm just telling you what problems you might face, and you have to be careful. You have to deal with that, and once you have this set of features as one-dimensional vectors, do some kind of vectorization, some kind of decent vector. For example, you can just blindly use TF-IDF vectorization, or do something. If you have a lot more time and tolerant to more pain, you can talk to the domain experts and get weights of individual features, relative weights of individual features, so that you can do weighted TF-IDF vectorization, so that this feature is more important than this feature, but less important than this feature, and stuff like that. So you can add certain weights so that the sum of the weights equals to 1 at the end. You can do that. And then you have to play around with these weights so that eventually it kind of converges and you get more or less good results in the future, stuff like that. So you can do that. So once you do all these things, then you get a beautiful TF-IDF matrix like this, or any kind of how do I say, this matrix is basically the matrix on the right side basically represents the importance of that particular feature in that document relative to the entire corpus. Okay. Once you have this, then you create the similarity matrix. Back to that same previous section. Ultimately you need a similarity matrix somehow, and you have to define your own distance measures and stuff like that. But you need a similarity matrix to move ahead. And with this TF-IDF matrix, you can basically generate a similarity matrix, similarity ranking based on TF-IDF. So basically you can multiply the TF-IDF with this transpose and get a similarity matrix. It could be a cosine distance or some other distance, but you have to experiment with the distance measures yourself. Every machine learning tool out there will give you a standard set of distance measurement functions: cosine similarity, Jaccard similarity, Minkowski similarity, and many other similarities they'll give you. You can try. If one of them works for you over a period of time on empirical analysis, if it works, great. Otherwise, you have to have your own distance matrix, and whether it should be metric based or non-metric based. When I say metric based, then it has to follow triangle inequality, right? If A is closer to B and farther away from C, then it has to eventually form a triangle. Otherwise, your metric is broken, and it won't give you the right distance when you really need it, right? So those kind of things, you have to be very careful there. Once you do that, you get a nice similarity matrix, and once you have similarity matrix, the same procedure. Get clusters, and the cluster evaluation you can do in very different ways. I will briefly talk about cluster evaluation. Before that, let me see. Okay, here is the summary of hybrid-based clustering. So you have these samples, run it through Cuckoo Sandbox. You get analyzed JSON files, and these files, from these files, you do feature extraction. Once you get the features out of it, you generate the corpus. The corpus will be represented in a nice big matrix with floating point numbers in it. From that corpus, you generate similarity matrix, and from there you cluster. And once you finish clustering, then you can do all the rest. All the fun things after that is evaluation, reclustering, finding out anomalies within a cluster, finding cluster density, trying to find centroids of the cluster. And if the centroid is a member, then great. If it's not a member, you have to average it. And then once you have a centroid, nice centroid, then you will know the salient features of the cluster. And then you can just monitor the cluster every month or every quarter. If you had monitored a particular a particular cluster over the past 3 years and say every summer this guy hits, he's very prevalent in Asia Pacific. So I know what you did in the last 3 summers, and probably I would know what you would do the next summer, some stuff like that. And you would already have a nice signatures readily designed for it, right? Stuff like a lot of nice things could be done. You can basically find out which clusters or which family of malware were prevalent in early 2006, then faded off in the summer, and then came back in late 2017 or whatever. You will know that. You can find the lineage of a given. Once you have, let's say you have one cluster, you can find the lineage within the members of the cluster. Which malware within that cluster was the seminal malware, and how it spread out, how the variants came, which were the first hop variants, second generation variants, and stuff like that. You have a lot of beautiful things could be done with it. Questions? Yes?
So I wanted to go back to that slide. I had a question specific, sort of after this question.
This one?
Yes.
Okay.
So
this is kind of a dumb question, I'll admit, because I'm not an
Questions are
expert in this
never
kind
dumb,
of
only
stuff.
answers are.
So this seems very sensitive to feature evaluation, right? Like if you choose the wrong set of features, you're not going to get very good like cluster generation. If you choose the wrong clustering algorithm, right, it's not going to spit out very useful information. So you've got this going, you're feeding it data. How do you know that it's working? Like how do you know that you're identifying the right things, and how do you iteratively go back and improve like your feature extraction and clustering and so forth as you do this?
It's a painful process. I'm a data science guy. I'm not a security researcher. I have limited exposure to malwares and their behavior. So what I do is this. So I have the first is visual examination. Once I have the clusters, I look at the members of, let's say a cluster has 7 members in it. I manually look at the JSON files of these 7 guys. Manually look at them, compare line by line, feature by feature, section by section, and validate myself. Hey, they look good. And then I just give that 7-member cluster off to the malware researchers and tell them, hey, I found these as, these 7 as variants of the same family. And they will say, why the hell this member number 5 came there? That shouldn't be there. Then I will go and argue with them. Hey, look at their JSON files. They all look the same. And that guy will come and say, hey, no, Cuckoo Sandbox was run only for 3 minutes. That, in 3 minutes, this guy didn't do much at all. Even though he had the similar traffic, if you run the same Cuckoo Sandbox on this member number 5 for next 30 minutes, he would have done all these different things which no other guys would have done it. So essentially, you are defeated. Then I say, come on, then run all the samples for 30 minutes. Then he'll say, I don't have the resources. That's why, in most cases, this is good, but you can go back to opcode clustering. Opcode clustering never lies, doesn't lie at all, because you have the opcode, all the instruction sets. You know what it will do. Even you don't have to run it. You don't have to execute it in a Cuckoo Sandbox. So this is one thing. So, but again,
then
I mean, the
isn't your
problem
op-
is it's, sorry.
Isn't then your opcode thing though? There's obfuscation and so forth that could come into play
There are
that might
techniques, there are
mess with that
techniques
too.
There are nice mathematical techniques to lessen the problems of, you know, obfuscation techniques. So, yeah. Did I kind of answer your question, sort of? Okay, okay, okay. Yes.
So, just out of curiosity, it sounds like this is more of research, but do you have something which is working currently that we could probably try to use and try to test it?
This is working. I don't have a demo, but this is in fact working. Yeah.
But I mean, is it available like in GitHub or something where we can get a hold of and try to?
It's mostly internal, but the concepts are all, it's out there. This is no secret. I mean, these concepts are probably there for 4 decades or so, so it's no secret of it. So, yes.
With that being the case, and the sort of primitives being well known, it seems like kind of to his point that the key thing is feature selection. So to what extent can you kind of talk to the features that you find the most useful in doing this kind of analysis? Is that kind of a proprietary question?
It is. I mean, it is an IP actually. So, in most companies, for example, which does data analysis, ultimately it boils down to the data they have and how they choose the data and how they correlate the data. That's an IP for them. It is.
Not even a top 10
If I tell that, then you'll kick me out because these are well known. For example, I rattled out, right? Lack of a referrer, which is a key thing. And how are you going to deal with it is something secret, right? Then having, okay, for example, user agents, right? You have a lot of these user agents present, right? So how are you going to find the needle in the haystack about a user agent? How are you going to provide it a weight, relative weight? It's not an absolute weight, it's a relative weight, right? How are you going to do that? So so let's say you are sitting with a mountain load of historical data sets, then you can have a very fast key value database to search over all the previous user agents, put them in a Bloom filter, and quickly check whether it is there or not. And if you find a low probability of that, then you can say, hey, this looks interesting. So essentially, what you are trying to do is look for interestingness in your current data, based on prior data and other factors, right? So, and once you find that this is interesting, then you have to score it, some kind of interestingness score from 0 to 1, right? So there has to be some net score, but before you arrive at the net score, you have to score for individual attributes, and then come up with a net threat score. Hamming distances are different.
Okay.
There are various ways to score. Essentially you have to come up with your own scoring mechanisms, but that's it. I mean, there are nice clues in literature, but you have to try out. It's hard. No, I'm trying to be as explanatory as possible, but it's not like, it's not like a cookie cutter thing, like 1 + 1 is equal to 2. Just trust me. I can't do that. I can't say that. Questions? Thank you.